Hey Rick, how are you doing?
Hey, how you doing?
Yep, pretty good. All right, let's see. Okay, let's see over here. Let me pull up a module. Oh, should go. All right. Internet over here is a little bit slow, but let's see. Share screen. Okay. Not this. Artificial 302. So we're on the last module, right? Yep.
Right.
You can hear me, Rick? Oh, okay. All right. Just checking.
Can you hear me? Is everything
Okay.
good?
Yeah, I can hear you. Yes, I can hear you.
Oh, yeah, it's
Yes.
delayed.
It's delayed. Okay. Let me see if I can turn off my video. Okay, there we go. Maybe that will help a little bit.
Can you hear
Uh,
me?
uh, um, yeah, I can hear you. Yes.
Yeah,
Not sure why it's being delayed.
like the audio, it's like when I speak to you and then you reply is like a 1 to 2 second delay, I think.
Okay.
Yeah, it's just
Okay,
extra
you
delay.
can try turning off your video. See if that helps with the transfer rate. Okay.
Can you hear me?
Yeah, I can hear you. Yes.
Yeah, it's not as delayed now. That's weird.
Okay. All right. And you can see my screen, right?
Yes.
Okay. So we are on module number 5. And if I go and check on lab assignment, let's see. So module number 5, I think it has a bunch of other performance tweaks. Yeah, this Zybox is running a little bit slow. But one of the things in module number 5, I believe they talk about is PCA somewhere. There we go. Here is PCA. So today we'll be looking into PCA, which stands for Principal Component Analysis. And what it means is that sometimes we're looking at features, lots of features, lots of different columns, and we don't know that how those columns affect the actual model that we are going to be creating. Like you can have like 100 different features, but what, like, which one of those features are actually producing or changing the model performance? So today we're going to learn a technique which is called principal component analysis, also known as PCA, which kind of helps you give you less features, and then we can try to see if that helps with the model generation. Sometimes those features are important. I mean, if you are trying to find out the house price, so you may have features like number of bedroom, number of bathrooms, is it close to the city or how close to the school? Now, all of those features are very important, but sometimes you will have features like, well, what kind of a tree is in the backyard? Okay, so that doesn't really matter with the value of the price in most cases. So PCA can be used to create new feature columns or features based on the existing features uh, to improve the performance in certain cases, not in all cases. All right. So that is something we're going to be looking at. You can hear me okay, Eric, right now?
Yes.
Okay, good. So let's take a look at an example. And the example we're going to look at is the built-in one, which is the digits. The digits, handwritten digits, how we can use PCA to use with less features. And we'll see, maybe PCA will do a good job, but maybe it can do a bad job. Maybe it will suggest that, well, you're using so many features, maybe you shouldn't be using. You should use like 2 features instead of 20. But sometimes it's not correct. So, but still we should know how PCA works. So I'm going to start with importing the lower digits, which is already built into scikit-learn. We will also import pandas. And then we can simply call lower digits function, which can give us basically all the handwritten digits. You can also go ahead and call the keys function, which basically prints out all the different keys for digits. You can see its data, target, frame, feature names, target names, images, description. So you have all of these different keys or properties that you can use. And you can also find out data. The data is the one that contains, digits of data if I print it out. That's just the representation of the actual digits in the form of 0 to 16 pixels. And this is what it looks like. It's kind of like is it like a two-dimensional array or something? No, sorry, it's a one-dimensional array with, let's see the shape of it. Shape means that we can always check that how many rows and columns are there. Okay, so there are 1,797 rows and 64 columns. So 64 columns is, that's a lot of features. And if you see this, there are some columns that are just, probably they're just 0 all the time. Like they don't really contribute to anything. Like if I go ahead and say digits dot data of 0, I can see some of these columns. Okay, they look fine. But some of these columns, if I will eventually see, you will see that those are like just zeros. It's a good idea to always plot in a graph or view these things in using matplotlib, so we will have a little bit more idea. But the problem with this array is that it's a single dimensional array, and when you want to use matplotlib, it requires 2-dimensional array. So I will have to somehow convert it to 2-dimensional. But that's not a big deal because we can always use like this, the first item, and we can reshape it to 8 into 8. Why 8 into 8? Well, that's because we need to get to 64. That's the total number of columns. And 8 into 8 will make it 2-dimensional, which will have 8 rows and 8 columns. And now you can see it's a little bit different. You can see that now it's 8 rows like this, and the columns are also 8. And if you look at the first column, this doesn't really mean anything. I mean, it's just the first column is just 0 bits or 0. I mean, nothing there, like a 0 bits, meaning it's empty. So how is this even contributing to the classification? I mean, we'll see when we plot something out, we may get to look like. So let's go ahead and plot them. Matplotlib, py plot, splt, and we'll say matplotlib inline plt. If we want to see an image, we'll say mat show, and then we'll simply pass in the image that we want to do, but as a two-dimensional array. So we have to reshape it to 8, 8. Now this shows us a color image. So probably it might be a good idea to just look at the plt.gray, meaning look at the image in gray. Okay. Now, if you're looking at this image, you might be wondering, what is this box actually doing? I mean, all of these boxes, they're just, black. They don't really contribute anything to finding out that this is a 0. I mean, it is a 0, but what are all of these things doing? I mean, how are they even contributing? And that is what the PCA is all about. PCA is going to be looking at the data, and it's going to decide that, do we even need these columns? I mean, do we even need this stuff? What if we remove this stuff? I mean, it's definitely going to increase the performance, because now we don't have to go through all of this stuff, which doesn't really contribute to anything. This is fine because there is a little bit of a shade going on over here, but all of these things, they're not fine. So why don't we just, remove them? This will definitely improve our performance. And this is for everything. If I go and check number 9, I guess that is 9, the actual number 9. It has the same issue. I mean, these are just a lot of space that is not really contributing to anything. All right. So let's go ahead and see how, or what can we do with the PCA. But before we do that, it's always a good idea to look at our data apart from looking at it in a graph or using matplotlib. It's also a good idea to look at it in a data frame. So we can say pd.dataframe digits.data, because we want to look at the pixels, and columns will be equals to digits.feature names. So whatever the feature names are, you should graph those columns. Oops, let's see what's going on over here. Okay, maybe I have to do this, df.head. So this is what this looks like when we convert the data, which is basically array of numbers, pixels, into a data frame. You can already see a couple of different things, that how are they contributing? I mean, they're all just zeros, like pixel, like look at this one. All of these are just, this one is not, but most of them, how are they actually contributing to these things? Some of them may not be 0. I mean, I'm printing out only 5 of them, but like maybe this one, all of them are 0. This one maybe, which basically means that, I mean, it's not really contributing to telling us that this is a 9 or this is a 0. So this is where we can try a little bit to use PCA to try to do something in that case. All right. Any questions at this point?
No questions.
All right. Let me see. I think my display is not working. Okay. Okay. All right. I don't know what's going on. All right. Okay. And you can also call a function on the data frame, which is called describe, which gives you a little bit more, and I think we can look at it, sticks. So this means that this is going to give you a little bit more description, or so we can actually see that feature number 0_0 count is 1797, and 1797 is obviously for all of them, they are the same. Then we have the mean, minimum, maximum, all of that stuff. So we can kind of like look at all of that will tell us anything. I think this kind of tells us a little bit that pixel on the first location of the two-dimensional array, that's a 0. So I don't know how they're contributing to everything else. It has some numbers. So maybe that whole column 0, maybe we don't even need that. All right. X equals 2. Now we were going to scale them. So what does that mean, scaling? Well, a couple of different things we see over here is these numbers are a little bit like there's a distance between these numbers that we have, 0.3, 5.2 something. So they have a bit of a difference, like when we look at these numbers. And scaling is going to allow us to bring them a little bit closer so that machine learning algorithm can function on it without a big error. Like if something is like it costs $75,000, another house costs 85,000, then another house costs 100,000, then another house costs 750,000. That's $750,000 house is gonna mess up everything because now the scale is just gone crazy from 75,000 to 750,000. So what we want to do is to scale them in a way that they're all kind of like within the reach. So let's see how we can scale stuff. But before we do that, let's put x equals to df, y is equals to the actual target, which will be the actual numbers. And now we can try to scale them. So how do we scale them? Well, we use something called sklearn.pre-processing, and we import standard scaler. Then we create an instance of standard scalars. We don't really want to scale the actual prediction because the prediction is from 0 to 9. We don't really want to do that. I mean, we're only scaling the actual independent variables, which is transform x. And if we want to print out x scaled now, you will see that these are scaled. Now the array, and if I print out also the other array, let me add over there so that we can see the original one, x.head and xscale.head. So this is what the original looks like. You can see numbers like you have 5, you have 4, 13. Okay. But when we scale them, what happened over here? Oh, this is a NumPy array, so maybe that's why. Okay, so it's not a data frame, it's a NumPy array. You can see that they're a little bit more closer now, or at least the values are smaller. And I think most of these values, you can see that some of them are actually negative. Why are they negative? Well, because it needs to find the mean and then subtract the mean from each number. So maybe the mean will be, the center value would be, let's say 5, right? And then it will say 5. will be obviously 1, or 4 minus 5 will be minus 1. So that's why I end up with scaled. And it's always a good idea if to scale the values so that your machine learning algorithm can work on the scale value. Now we can use sklearn. What are we going to use? Split, train, test, split, and X train, X test, Y train, Y test. Again, train, test, split. We're going to pass in the scaled as a X, and Y will be just Y, and the test size will be 0.2. Now it's up to us what kind of algorithm we want to use. Now, since we are trying to find out classification, whether the handwritten number is 0 or 1 or 2, we can use some sort of a algorithm over here, which is logistic regression. That's one of them. So sklearn.linear model, import logistic regression. We're going to import that. We can go ahead and create an instance. We have already done that number of times. X train, Y train, and let's go ahead and try to find the score. So score, X test, Y test. So it's coming out to be 96. Okay, that's fine. Right now, that's just our basic thing, right? I mean, we haven't really used PCA, by the way. It's just how you would, we just scaled it, which is always a good idea, but we haven't really used PCA. And keeping in mind how many columns did we had, like the feature columns? Let's go ahead and see. What, 64? 64 columns, right? So this means we have 64 columns. Yeah, you have a question, Rick? Can you hear me, Rick?
Now I can. It cut out for like 5 seconds.
Oh, okay. All right, let's see. That's weird. I mean, the internet speed is not that slow over here. Okay. Okay. So we have our score of 96%, but we haven't really, we have how many columns? 64 columns. So we have 64 feature columns. Okay. With 96% score. Okay, so that's fine. But can we reduce those columns? I mean, if I simply look at X, yeah, that's a lot of columns. You can see 64 columns. It just goes on forever. That's a lot of columns. And this is a real life situation because when you're doing machine learning, let's say you're trying to find out the price of a car, somebody can give you like 100 different feature columns, but we will have to find out that if those 100 feature columns are even contributing to getting a high score or not, or they are just there for, some random columns, garbage columns that we can delete. So let's go ahead and try to use PCA, and maybe PCA can help us out a little bit. Maybe it can't, but we'll see. So we're going to use sklearn.decomposition. We're going to import PCA. All right. And after this, we will have to tell PCA that how much columns or how much features do we have to keep intact. Meaning, if I say PCA 0.95, let's see over here, maybe they will show us some definition over here. And components, all of this. So components actually 0.95 means that we want to keep 95% of the features. So don't, just use 95% of the features and try to see if we can get a good score. So we'll say xPCA, PCA dot fit transform X. And let's go ahead and see xPCA dot shape. Okay, so we got 29 over here. And we have 64. Let me actually double check this because I thought that it's gonna, let me see what is actually 95 means. Like it's, let me just double check what it means actually. Okay, let's see. Parameter used to pass PCA when you instantiate, whether you're telling the algorithm to choose the number of principal components, such as 95% of the variance in the data is retained. Okay, 95% of, so this means that 95% of the feature set is retained. Okay, instantiate PCA with retention. Okay, I guess it, so 95% of the features are retained. I guess that's what it means. And you can see the shape is coming out to be 29 instead of 64. So this means that it has reduced the number of features to 29. And by reduce, it doesn't really mean that it has created new feature columns based on the original ones. So it does not mean that it has reduced it. It simply means that it used the 64 columns and it used their values to create 29 columns, which provide some data. But the big question is this going to allow us to have a better, better score? Can we get the same score, 96%, if we are, if we are doing like 95% of the features, all right? Or retaining 95%. So let's see, what are 30 and 64? Okay. So let's see what we can do over here. Again, we're going to start with training. So xtrain, PCA, xtest, PCA, ytrain, and then ytest. Because now we have x underscore PCA, which is composed of 29 different feature sets, feature columns, instead of 64, which are the original. Does that change our score? If it doesn't change our score, then we can just use 29 column. We don't need all of those, 64 columns. It's going to be much better for performance. Okay, for training, I guess this is, XPC is fine. And I guess the other one is simply way, and test size is 0.2.
Think the screen might be frozen on my end.
Okay, we're gonna do the same thing again. We will have to, test it out, like into some other stuff.
Hey,
I
can
don't
you
know
hear
when
me?
you. Not sure what happened over there. Shared screen. Okay, you can see
Okay,
the
there we
screen now,
go.
I guess. Yeah.
Yes.
I'm not sure what's going on. The internet over here is not that good, but it's only for one day, hopefully. Then I'll be somewhere else. Okay. All right. So we have to train it again. So we have now 29 feature columns instead of 64. We're going to use the same algorithm, which is logistic regression, because we are classifying it. Model equals to logistic regression. Model equals dot fit x train PCA. So this time we are using the PCA x train data because that only consists of 29 iteration something. Okay. So at this point, we have trained it. We can go ahead and try to see if that is good or not. Well, it's close, as you can see, right? The original percentage with 64 column was 96%, and with 29 columns is 95%. So I guess what we should be asking is, well, do we need all those rest of the, what is it, like the 15 columns, like 15 feature sets? I mean, they didn't really make that much of a difference. Probably those were the columns with zero value. Okay, so we get the same result even though we use less features. Now, what if we go in a different route and we only say that we want to use two features? How will that work, right? So if I say PCA, and components, we're just going to use two components. Two components over here means that we're just going to be using two features in order to find out that if the text, I mean the image, handwritten image is a 2 or 3 or any of a number. So we're going to use two. And then we're going to again try to see this, XCPCA. What do you think, Rick? Do you think the percentage will go up or down? The score will go up or down if we just use two features?
It's definitely going to go down.
Right? Oh, so let's go ahead and see. Let's first make sure. Okay, number of rows are 179, the same, but now you're only saying that it's
I can barely hear you. You're breaking up a
going
lot
to
for me.
number of rooms. columns which will be columns. So it's these features will featured. Now, can you hear me now?
Hey, can you hear me?
Uh, yeah, I don't. Yeah, I can hear you.
Yeah, yeah, it just seems like
Can you hear me?
yeah, I can hear you now. It seems like the connection's just going in and out.
Going in and out. Okay, all right. We have little. We can just do this. Like we can just try to test this out. The percentage. All right. And as you expected, a 0.60 instead of 95, 96%. So if we use less features in some cases, as you can see, score was logistic regression now doesn't have any other questions, right?
No, I think I understand. It's still going in and out. I could barely hear your question. I'm sorry.
Okay. Right. It keeps cutting off for some reason. All right. Let me see. All right. So I give you a link in the chat, and you can use that. You can try to see that is the code. All right, hold on. So what I'm going to do, Rick, I'm going to give you this code. Look at this later. Well, let me see. How do I turn off the video? Off recording